All right, lesson 15 is semi-log plots. So our skills and learning objectives are to use semi-log plots with the y-axis logarithmically scaled that show linear behavior from exponential characteristics, apply techniques used to model linear behavior to semi-log plots, and construct the linearization of exponential data. All right, semi-log plots are a useful tool for visualizing data that covers a wide range of values. A semi-log plot is a graph that combines a logarithmic scale for one axis with a linear scale for the other axis. It is used to plot data that covers a wide range of values where a linear plot would make it difficult to see the details. The semi-log plot will create a graph that reveals the details of the data while still showing the overall trend. In this lesson, we will learn how to create and interpret semi-log plots. So example 1 here says, let's consider the function f of x equals x on two different types of graph paper. So on A, we're going to graph the linear axis. On the linear axis, we're going to graph y equals x for the table below. And so we're just going to plot these points. And we're going to draw in our graph. B, they left off the B here, but the B says use a semi-logarithmic axis at the right to plot the graph y equals x. Notice that the vertical axis is a logarithmic scale base 10, so there are no negative values for y since we can't find the log of a negative number. The horizontal axis is a linear scale. All right, so look at your numbers on that y-axis. Let's look at it first. So notice we start out with 0.1, work my way up 0.2, and you can tell each line between it, and so from here to here, each line is a 0.1. And then notice between 0.5 and 1, these are also by 0.1s then, okay? But then from 1 to 5, these are by 1s, and so is the 5 to 10. So just when you're dealing with the semi-log graph paper, you need to watch the scale of that y-axis. All right, so when we go to plot our points, we're going to plot the points 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. So when I go to graph this, I can see it's doing this curve, and then we're going to have to curve downwards here. So what do you notice about the graph of the linear function on the semi-log plot? So it looks like that our linear function appears to be logarithmic. All right, at the bottom there, it says mathematically, we treat a logarithmic axis as a transformation of the variables. For our course, we will plot data pairs x, y in a semi-log plot where we are working with the transformed data pairs x, log y or x, natural log of y. Think about the log of y as a variable. The logarithmic scale is a great tool to compress a large range of data into a small space and be able to detect small variations in the values of the data points in a set. Example 2 says consider the function f of x equals 9 times 3 to the x. The table below shows the values of f of x at selected values of x. To graph this function, we would need a very long y-axis. However, if we use a semi-log plot where the y-axis is scaled to powers of 10, we can graph many of the function's values. All right, so I'm going to graph this. We got 0, 9. So we need to make sure that we're going to look at the scale, and it's really hard to kind of see because they're so small. But notice from right here, we go from 1 to 10. And then be careful because then we go from 10 to 100. Now they just labeled it as a 2, but what would it be if it was 2, 3, 4, 5, 6, 7, 8, 9, 100? Those, remember, are by tens, okay? So it's really 20, 30, 40, 50, 60, 70, 80, 90, 100. And then notice here we're going from 100 to 1,000. So each of those in between are by hundreds. From 1,000 to 10,000, 100,000. So each of those are by, from 1,000 to 10,000. So each of those are by thousands. And then we go from 10,000 to 100,000 right there. So each of those are tens of thousands. So this right here stands for 20,000. This would be 90,000 because the next one up is the 100,000. So make sure you're looking at those scales so you can understand them. So when I go to plot the point 0, 9, x is 0, my y is 9, right before the 10. 127, so I've got where my x is 1. Remember, this is 20, this is 30, so it's going to be somewhere in between, closer to the 30. 2 and 81, so I'm going to go to 2. Here's 80, so it's going to be just a little bit more than that. Um, 3 and 243. So 3, so here's 200, here's 300. So my point's going to be somewhere right in between them. 4, 729. 5 is 2,187. So here's 2,000, here's 3,000. 6, 65, 61. Oh, sorry. 7 is up at 19,683. So make sure you're finding where the 19,000 is. Here's 10,000. Here's 20,000. So it's right before the 20,000. And then 8 and 59,000. 59,000 is almost 60,000. And then we're going to connect those points. All right, B says, what do you notice about the graph of the exponential function in the semi-log plot? Well, if you look at that graph, you should notice that it appears to be linear. All right, C says to write log base 3 of f of x in the form of log base 3 of f of x equals mx plus b. State the values of m and b. All right, well, we know that f of x, it told us at the very first part there, is equal to 9 times 3 to the x. Well, we've talked about that as long as what we do to one side we do to the other, then our function stays equal. So I want it to be log base 3 of f of x. So I'm going to log base 3 the left side, which means I'm also going to log base 3 the right side. Can't do anything on the left, so I'm going to work on the right. I can expand that right there because they're being multiplied. I can separate them through addition. So log base 3 of 9 plus log base 3 of 3 to the x. Log base 3 of 9 I can work out. So I'm going to come over here. So log base 3 of 9, log base b of x equals y. And we change it to b to the y equals x. So 3 to the y equals 9. So 3 to the y is 3 squared. So we know that that is equal to 2. And so this is 2 plus, and then remember, we can take that x and move it as the from the exponent to the coefficient. So that's x log base 3 of 3. And then we know that log base 3 of 3, either we talked about this the other day or you could work it out. So 3 to the y equals 3 to the first. So we know that that is equal to 1. But remember we had said if our base and our base of this part are the same, then we know the function is equal to 1. So we end up with just 2 plus x. And so we know that log base 3 of f of x is equal to 2 plus x. All right, it says state the values of m and b. Remember, m is your slope, so it's going to be a 1, and b is your y-intercept, which is 2. And D wants us to graph this relation with log base 3 of f of x as the vertical axis and x. Hold on, let me try that again. We're going to graph this relation with log base 3 of f of x as the vertical axis and x as the horizontal axis. So we're just going to graph our line here. So we know that our y-intercept is at 2 and our slope is 1. And so that is our graph. All right, example 3, plotting functions on semi-log graph paper. It says given g of x equals 8 times 2 raised to the 2x, find the values of m and b such that log base 2 of g of x is equal to mx plus b. Graph log base 2 of g of x equals mx plus b on the graph provided. Label the axis appropriately. All right, so we're just doing like what we did on C, on the previous one. So we know that g of x is equal to 8 times 2 to the 2x. And it told us it wants to take log base 2 of g of x. So that means we're going to take log base 2 of 8 times 2 raised to the 2x. Then we know we can separate what's in the parentheses because it's being multiplied. We can separate it by addition. So log base 2 of 8 plus log base 2 of 2 to the 2x. Log base 2 of 8 we can go work out. We'll find that it is equal to 3. Plus, we're going to move that exponent as its coefficient. And then we're left with log base 2 of 2. Remember, these two are the same, so we know that log base 2 of 2 is equal to 1. And so we end up with just 3 plus 2x. And so we know that our slope is 2, and our b, the y-intercept, is 3. My y-intercept's at 3, my slope is 2, so at 2, write 1. And then we can draw our line to graph it. Example 4 says given h of x equals 5e raised to the 7x over 3, find the values of m and b such that the natural log of h of x is equal to mx plus b. So it's just more of the same. So they told us that h of x is equal to 5e to the 7x over 3. And so we're going to take the natural log of h of x, which means we're going to take the natural log of the other side. And we're going to work on that right side because these two are being multiplied. We can separate them with addition. So we got the natural log of 5 plus the natural log of e to the 7x over 3. I can't do anything with the natural log of 5. It doesn't work out. So I'm just going to leave that as a natural log of 5. Plus, but we know we can move that as its coefficient. So 7x over 3, natural log of e. Natural log of e is just 1. So we have the natural log of 5 plus 7 over 3x. So we know that our m, our slope, is 7 over 3, and our y-intercept is the natural log of 5. If I was going to graph this, I'd be able to put natural log of 5 in my calculator and find that it is approximately 1.609. And then example 5 says, given the function y equals 3e raised to the 0.5t, A wants us to find the natural log of y and plot the data t comma natural log of y on the grid provided below. All right, so they gave us t, they gave us the y value, and we want to find the natural log of y. All right, so they gave us t, they gave us y, and now we're just going to find the natural log of that y. So we're going to type in our calculator the natural log of the y, which is 3, and it's going to tell us 1.099. The natural log of 8.2, 2.099. The natural log of 22.2, 3.099. The natural log of 445, 6.099. And the natural log of 66,079, and it tells us 11.099. And so we're just going to plot this data, but it wants us to plot t comma the natural log of y. So we're going to plot those two columns. So when t is 0, my natural log of y is 1.999. When t is 2, it's 8.22. I'm sorry, I'm looking at the wrong 2. It's 2.099. At 4 is 3.099. At 10, 6.099. Oh, my points are so off. I'm so sorry. Here we go. 1.099, 2.099, 3.099. We said 10 was 6.099. And 20 is 11.099. All right, we're going to connect those points. These is to find a linear regression model. Y hat is equal to ax plus b for the graph. All right, so looking at it going from 0 to 20, we can find our m and our b. And so m, I'm just going to use my slope formula, which the y value there, I'm going to use the natural log of the 66079 instead of putting the 11.099, because 11.099 was a rounded value. So this is going to get me a little bit closer to the exact value. Minus, that's my, so I guess I'm finding the slope between these 2 points, okay? Minus y1, which is the natural log of 3, over x2 minus x1. And so when I do this, I get 0.4999 repeated. B is our y-intercept. So it's when that t value is, or our x value, in this case a t is equal to 0, which is at that 1.0986 or 1.099. Round it correctly. And so we know then that our equation is going to be the natural log of the y hat will equal the m x plus the b. And then C says to use your calculator to find the linear regression model to verify your equation. So we're going to go put this into our stat edit. I'm going to put my t's in L1. I could even put my y's in L2. So L1, I would have that 0, 2, 4, etc. In L2, I'm going to put my y values, the 3, the 8.2, the 22.2, and all the others. And then in L3, I'm going to go up on L3, and I'm actually going to type in that spot right there the natural log of the y, which is what we put in L2. When you hit enter, it's going to start putting these numbers in for you. So you don't actually have to even type these in, okay? Now, when you go to do your stat calc, so you're going to go to stat, go to calc, over to calc, then you're going to go down and you're going to pick that linear regression. So number 4, lin reg. Now your x's are in L1, but your y's are going to be in L3. And remember, you can get that by hitting second and the 3 button. All right. And then find your equation. And you should get that y is equal to 0.5x plus 1.0986 as your equation. All right, example 6 says consider the data in the tables below. Determine whether the data can best be modeled by a linear, logarithmic, exponential, or power regression equation. Explain your choice and support your answer with tables and graphs. All right, so when I look at on A, I notice that my x's are each increasing by 1. And I notice that my y's here are increasing by 3, by 3, and by 3. Because my slope, my change in the y over the change in the x is constant. It's increasing by 3 over 1 each time. That's going to mean that it's linear. Check it on B, so we can see that our x's are each time it's increasing by 1. And here my y's are increasing by 6, by 12, by 24, which means they're just being multiplied by 2 each time. So instead of saying increasing by 6, we could say it's times 2. 12 times 2 is 24, times 2 is 48, because the y is increasing by a factor of 2. By factor, remember, means it's being multiplied. That means the base of it would be 2, so therefore it's going to be exponential. All right, on C, my x's are increasing by 1. My y has an increase of 1.4, and then increase of just 0.8, and then increase of 0.6. We notice our y is still increasing, but it's increasing at a decreasing rate. So it's increasing at a decreasing rate. And so remember, if you're thinking about a graph, what that would look like is we're still going up, but we're not going up as fast. So that also means that it's concave down. And so that function looks like a logarithmic function. And then D, my x's are increasing by 1. My y's is decreasing by 6.5, decreasing by 3.25, decreasing by 1.625. Or if I notice, since these numbers are the same, they're decreasing by half each time. So the change in y is decreasing by a factor of 1/2, which means this is exponential. All right, and that is the end of 15A. Lesson 15A.